Welcome back to this course on multi-core systems. In this lesson I will describe the basic directory protocol called the full directory protocol. For each memory block, this protocol keeps track of which cores or nodes have a copy of that block. As in snooping protocols, we must also keep track of the state of each cached copy of a block. For that we will use the baseline MSI protocol. To recap, each block can be in one of three states. Invalid, which basically means the block is uncached, which in turn means that the cache doesn't have a copy of the block. Second, shared, which means that this cache has a copy, but also other nodes can have a copy. And third, furthermore, it also means the memory copy of the block is up to date. And third, modified or dirty, which means that this cache has the only copy and the memory copy is outdated. Therefore, other nodes that want to read or write this block have to come to me. Me being the node that has the block in state dirty. The node that has the only copy of the block in state modified is sometimes called the owner of the block, even though it is a bit confusing since the Moesi protocol has this own state which has a different meaning. The textbook shows the state transition diagrams for the basic full directory protocol. In my opinion, these state diagrams provide too much information and therefore it is difficult to see the forest for the trees. Therefore, I will show different diagrams showing the messages that need to be sent between the local, the requesting node, the home node and potentially one or more remote nodes. I will do so for read misses, write hits and write misses and also do it for different cases. First, a read miss to a clean block. Since the block is clean, the memory copy at the home node is up to date. First, the local node, the requesting node, needs to send a read miss message to the home node, since the home node knows who has the most recent copy of the block. The home node now checks its directory and finds that the block is clean. Then the home node does two things. First, it sets the presence flag of the local node and it sends back the cache block data to the local node. Upon receiving the reply, the local node can allocate the block in its private cache in state shared. That covered the case of a read miss to a clean block. Now let's consider the case of a read miss to a block that is dirty in a remote node, like here. The first step is the same. The local node sends a read miss message to the home node. Upon receiving this message, the home node checks the corresponding directory entry and finds that the block is dirty at a remote node. Therefore, the home node sends a remote read message to the remote node. Note that the message type must be different since the read miss is directed at the home directory, whereas the remote read is directed at the cache controller. The hardware has to be able to distinguish these message types since the remote node is also the home node for many memory blocks. Upon receiving the remote read message, the remote node does two things. First, it changes the state of the cache copy from modified to shared, and second, it replies the block data to the home node. Then the home node does several things. First, it writes back the block to its local memory so that now it is clean again. It clears the dirty bit and it sets PL to indicate that after the transaction, the local node also contains a copy. Note that the presence flag for the remote node was already set. Finally, the reply is forwarded to the local node, to the requesting node. The local node can now insert the block data in its private cache in state shared. The previous two slides covered read misses. Let's now focus on writes. First, a write hit, meaning the block is in state shared at the local node to a block which has no additional copy or a single copy at the home node. First, the local node sends an invalidate message to the home node. Upon receiving this message, the home node sets the dirty bit. The presence bit for the local node has already been set, since a write hit implies that the home has a cached copy of the block in state shared. Furthermore, if the home node also has a copy of the block in its cache, the cached copy needs to be invalidated and the corresponding presence bit cleared. Finally, the home node sends back an invalidation acknowledge to the local node, and the local node can now complete the write and change the state of the cache block to modified. Now I consider again a write hit, but now there are one or more remote nodes that also have the copy of the block cached in state shared. All of these copies need to be invalidated. Again, first, the local node needs to send an invalidation message to the home node. Here there is no difference to a write hit with no additional copies. There can't be, since the local node doesn't know. Only the home node knows the status of the block. Upon receiving the invalidation message, the home node checks the presence flag. It determines that there are several remote nodes, which I indicate R1 to Rn here, which contain a copy of the block. So it sends all of them a remote invalidation message. This invalidation message has a different type than an ordinary invalidate message, so that the remote nodes can distinguish between an ordinary invalidate message, which is sent to the home node, and a remote invalidate message, because different actions have to be taken upon receiving them. Upon receiving a remote invalidate message, each remote node invalidates its copy of the block in its cache and sends back an invalidation acknowledge to the home node. Upon receiving all these invalidation messages, the home node clears all presence bit associated with these remote nodes and sets the dirty bit. And finally, the home node sends an invalidation acknowledge to the local node, thereby informing the local node that all other copies have been invalidated. Actually, to be 100% correct, this acknowledgement also have to have a different type than a remote invalidate acknowledgement, since they require different actions. But for simplicity, I have not indicated this on this slide. Finally, the local node changes the state of its copy to modified and completes the write. Finally, I consider a write miss. Again, I distinguish between two cases. The first case corresponds to a write miss to a block which isn't cached anywhere, or it is cached only at the home node. The second case corresponds to a write miss to a block that is cached in several remote nodes. This slide covers the first case, a write miss to a block which isn't cached anywhere, or it is cached only at the home node. First, the local node needs to send a read and invalidate message to the home node. So the local node wants to get a copy of the block and to invalidate all other copies if they exist. Upon receiving this message, the home node sets the corresponding dirty bit as well as the presence bit associated with the local node. If the home node has a copy of the block in state modified, it first needs to write back this data to its local memory, since it is the most recent copy, and invalidate its cache copy. Furthermore, in that case, the presence bit associated with the home node also needs to be cleared. Finally, the home node sends back a reply message containing the block data to the local node. Upon receiving this message, the local node allocates the block in its cache in state modified. Note that this may require another block to be evicted from the cache. If the evicted block is in state modified, it obviously needs to be written back to its home node. In any case, the home node needs to be informed. Finally, a write miss to a block that is cached in one or several remote nodes. Again, two cases can be distinguished that require slightly different actions. The first case is when the missing block is in state shared in one or several remote nodes. In that case, all the remote copies need to be invalidated, similar to the case of a write hit to a block with multiple copies. The second case is when the block is dirty, in state modified in a remote node. In that case, the local node needs to get the block from the remote node. I leave these cases as an exercise. The previous cases have provided you with sufficient information to draw the correct coherence transactions like I did before. We also need to specify what happens when a block is replaced. I already touched upon this issue 2 slides ago, but let's consider it in somewhat more detail. Obviously, when one of the blocks in the set is invalid, it can be replaced without any further action. So if there is the choice which block to replace, this is always the best option. On the other hand, if the victim block, the block that is replaced, is dirty, then the block needs to be written back to the memory of the home node, and the home node needs to clear the appropriate bits. These bits are the dirty bit, which must have been set because the block is dirty, and the presence bit associated with the node that needs to replace this block. All other presence bits must have been cleared already, since as said before, only one node can have the block in state modified/dirty. If the victim block is clean in state shared, then there are two options. The first option is to do nothing, as we do in a regular single core write-back cache. In a single core write-back cache, we can do nothing, since the memory copy is up to date. The memory copy is also up to date in a multi-core write-back cache, but if we do nothing, the directory entry for this block at the home node would become erroneous. It would indicate that the node that evicts the block would have a copy, while in reality it no longer would. This implies that later, when the block is written, this node would receive invalidation messages for blocks it no longer contains, and therefore these messages would waste bandwidth. The second option, and probably the better one, is to inform the home node that the block has been replaced, so that the home node can clear the corresponding presence flag. This concludes this lesson. Thanks for watching. A problem of the full directory protocol is that its memory overhead can be very large. I will discuss this issue in the next lesson, as well as an optimization that reduces the latency of a coherence transaction. Hope to see you back.